Hello, this lecture will cover pages 72 through 79 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on describing logic circuits, Part G, Application and Design Examples. We're going to start out by looking at page number 72, Application Examples. This should be more interesting for you here as we get into this part of the course, because now we're going to do design. We're actually going to do something you can make money with. So, let's take a look at some of these examples we got, and I'll give you a procedure here as we go through this on how you take a specification and you end up with a logic circuit that you can build and sell. I want you to take a minute and stop the video and read the specification. Okay, now we're going to design the logic circuit using and, or, and inverter gates that will detect whenever the level in tank A or B is too high, at the same time that the temperature in tank C or D is too low. I want you to always draw a basic block diagram as a starting point. It gets your thought processes started out, and it's a simple diagram here. If you take a look, A, B, C, D, 4 inputs and 1 output. Sometimes you'll have 3 inputs and 1 output. Sometimes you'll have 2 inputs and 2 outputs, and 4 inputs and 3 outputs. But it defines your inputs and outputs. That's the main part of the logic design. These literals, A through D here, represent signatures. Now, as we go through this, I want you just to remember, if we wrote down tank A high for A, and tank B high for B, and tank C low for C, and tank D low for D, as we go through this design, you'll see that if we're writing these actual signatures out, which is what you would have on the circuit, it would make the simplification process with Boolean algebra unmanageable. It would just be too long and too drawn out. So after you get the logic diagram, the first thing you do is you go from your specification to a truth table. So if you turn the page, notice we have a worksheet there, and I already did some work here. I want you to notice what I did. The first thing you do is you go from the specification to a truth table. There are 4 inputs, so you're always going to have 2 to the n. 2, in this case, n is 4. 4 inputs, 2 to the 4th is 16. You're going to have 16 different combinations of inputs. And what I do is, and you don't have to do them in order, but everybody does, so you don't miss anything. You draw a truth table, and you start out with 0, 0, 0, and 0, 0, 1, and you count 0. That's a binary 1. Here's a binary 2. Here's a binary 3. And I separate groups of 4s with dashed lines. And here's a 5, and here's a 6. Here's a 4, here's a 5, here's a 6, here's a 7. Separate them. There's a 8, 9, 10, 11. You separate them, and here's a 12, 13, 14, and 15. Now, you read your specification. And what it says is, we'll go back and look, design a logic circuit using and, or, and inverter gates that will detect whenever tank A or B is too high. Well, where's A and B too high? A's high, B's high. There's an output. A's high, B's high, output. So we put fundamental product 1s in where the A and the B's are high. At the same time, the C and D sensors are telling us that the tank is too low. And the way it's telling us that the tanks are too low is the sensors produce a 1. So let's take a look at C and D. The 1, 1 here says that tanks C and D are low. C and D, that 1 means they're low. C and D means they're low. And C and D means they're low, but we already had this. This 1 takes care of 2 possibilities. When A and B are active, at the same time C and D are active. So our fundamental products are this 1, this 1, this 1, this 1, here, and here, and here. Notice there are 1, 2, 3, 4, 5, 6, 7 fundamental products, and by default the other ones are zeros. Now we have our truth table. We go from our truth table to the Boolean algebra. What I'm going to have you do is put in an intermediate step. This is a shorthand notation we'll use later. I want you to notice that the fundamental products of the midterms are 3, 7, 11, 12, 13, 14, and 15. So here's my shorthand notation. The output is equal to the sum of the midterms, 3, 7, 11, 12, 13, 14, and 15. We'll just hold on to that thought for now. We'll use these when we go to K-maps in the next chapter. But now, in this chapter, we have to use Boolean algebra. Notice that we have 7 fundamental products. 1, 2, 3, 4, 5, 6, 7. I numbered them. I put a number above each of these fundamental products. If you look at this, there's your 3. 0, 0, 1, 1. How are we getting that first fundamental product? Here it is. A is low, B is low, C is high, D is high. How do we get this second fundamental product, which is 7? A is low, B, C, D are all high. How do we get this third fundamental product, which is 11? A is high, B is low, C is high, D is high. In other words, B is the only one with the bar above it. And you can form the other 4. Now what we're going to do is we're going to use Boolean algebra to simplify this. What I did is I numbered these, like I said, group 1, 2, 3, 4, 5, 6, 7 midterms. Now don't associate that with these not midterms up here. I'm just saying this is the first group, the second group, third group, fourth group, fifth group, sixth, and seventh group, because I'm going to combine groups here. And you wouldn't otherwise know how to do this, but I'm going to take group 1 and 2. I can take group 1 and 2 and I can factor something out. I can factor out a bar CD. And I can take groups 3 and 7 up above, and I can factor out an ACD. And I can take groups 4 and 5 above, and I can factor out a B, C bar. And I can take groups 6 and 7 above and factor out an ABC. When I do that, do you see these expressions all go to 1? I mean, B bar or B is a 1. You already have that memorized. D bar or D is a 1. One of these has to be a 1, and it's an OR function. So I can just proceed through my simplification here, group these two, and then rewrite this by reflectively writing. And my output design is, the output is A, B, or C, D. And here's the implementation of it. Here's the implementation of it right here. But notice we're using only 2 of the 4 7408 gates. 7408 is a quad AND gate package. And we're wasting 50% of it. And here we're only using 1 of the OR gates in the 7432. Look at your specifications so you know what I'm talking about here. There's a lot of wasted stuff going on here. But remember what I told you in a previous lecture. AND OR topology is the same thing as NAND topology. So my engineer is going to redraw that circuit like this using all NAND gates, but he's going to draw this output NAND gate like a negative input OR. 1, 2, 3 NAND gates. Only 25% of the 7400 package is wasted. You're only wasting 1 of the 4. This is a better circuit down here. And you draw the output NAND gate like this because it's easier to understand it when you're troubleshooting it. In your mind, these bubbles can burst. And that output is, if you have a high here and a high here, or you have a high here and a high here, you better get a high there. If you don't, something's not working in that circuit. It's immaterial what the midterm level is. You just want to know input, output, and whether the circuit's working. If it's not, now you get involved with the input, and this has to be a low active input in here. That's all. Up here it was a high active input. We talked about that. Better circuit right there. The next example is on page 74. So I want you to take a look at example 2 on page 74. I want you to read it. And then I want you to, on your own, I want you to do a truth table, do a shorthand output for the expression, and then I want you to draw your Boolean algebra and reduce it. And see if you can work it out on your own based on my last example. I'd stop the video and I'd take some time and see what you come up with. I think you'll notice that the design of this example is the exact same as the previous example. It's just that specification is just worded differently. There's the design of the circuit, but it's the same as the previous circuit. It's just that the specification is a conveyor belt. Logic symbol interpretation. This is on page number 76. You can look in your book on page 98 here, but if you want to see where the author talks about this, but basically, look, you don't worry about what gate you have down, what gate you need. Here's a NAND gate, an OR gate, a NAND gate, an AND gate. What you do is you let the story of how you want the circuit to operate tell you what gate you have there. And this is tough for some students to understand, but I got 5 examples here. Let me show you what I mean. Let's say in a specification they tell you that you want a high temperature signal and an enable gone high, and when that happens you want a low output. Well, you just draw the gate. You draw what you need. So the story here is, in the specification, it's going to say, when I get a high temperature and I get a high enable, I want the output to go low. And you just draw what it is you need, and you look and say, what's an AND gate? Let's try this down here. What if the specification in example 2 says, when high temperature goes low, because it's low active, and enable goes low, I want the output to go high. Well, the specification is going to tell you that. So what the specification is going to tell you is this. It's going to say, I have a high temperature gone active low, or I have an enable gone active low. And in that case, I want the output to be high. And then you look at that and say, well, that's nothing more than an AND gate. The logic levels determines how you draw the gate. You figure out the type of gate you need last. Let's look down here. What if they tell you, this one's pretty easy. When alarm 1 happens, high active, or alarm 2 happens, I want the output to go to alarm. It's an OR gate. Down here, what if alarm 1, what if you have a low active alarm 1 signal? When it goes low, or the alarm 2 active, it's a low active, when it's low, it's a low active alarm signal. When it goes low, you want the output to go high. You draw the circuit and you say, well, that's an AND gate. But you draw it like this because it tells the story. Down here, what if they say you have a low active alarm, or a low active alarm 1, or a low active alarm 2? You want the output to go low active to drive whatever's out here. Don't worry about that now. You draw the circuit and you say, oh, that's an AND gate. But you draw it like that because it tells the story. On page number 77, I say generate a high level output called accumulator 0 when a 4-bit accumulator is equal to 0. This is a 4-bit register. It holds 4 bits. 0, 0, 0, 0 through 1, 1, 1, 1, all 16 possibilities. You can use a truth table and go through it, but sometimes it's just think of what you need. Remember the previous page. We want to generate an output called accumulator 0 whenever all of those bits are 0. That's going to go high. Well, look, when this is low, and this is low, and this is low, low active, and, I'm saying and every time, it's an AND gate, this is low. I want the output to go high. You draw the story and you look at it and say, well, that's a NOR gate. How about generate a low active output called accumulator 0 bar, low active, whenever a 4-bit accumulator is equal to 0. Same thing up here, except you want this to be low active. Well, when this is low, and you draw a straight line, not a concave line. I didn't say or. When this is low, and this is low, and this is low, and this is low, you want that to be low. It's an OR gate. How about design a 2-bit comparator circuit that will produce a high output called equal whenever 2 bits of register A equals the 2 bits of register B. Here's a 2-bit register. It can have a 0, 0, a 0, 1, a 1, 0, or a 1, 1, and here's another B register. It can have a 0, 0, a 1, 0, a 1, oops, that should be a 0, 1 in your notes. Yep. A 1, 0, or a 1, 1. I just want to produce an output that tells me when this is equal to this. Well, if you look at the next page, I go to the truth table, and here's my inputs. I have 4 inputs. You draw if you want to draw the simple block diagram, maybe it would be helpful to see, but it has 4 inputs and 1 output. You list the inputs. You can do this in any order you want to, but I did A1, A0, that's a 1 register, and B1 and B0. They're all combined together as inputs. You have 16 possibilities. You put them in order, 0, 1, 2, 3, the whole way down to 1, 1, 1, 1, 15. And then you go through here and you produce fundamental products when A1 and A1 and A0 match B1 and B0. Here, 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 and here. So, equal is equal to the summation of the midterms. What are the midterms? 0, 5, 10, and 15. And here's the Boolean expression for it. 0, 5, 10, and 15. You should be able to see that. You should be able to see this and this as the same thing. How do you implement that? This is the way I implement it down here. I implement it with all NAND gates. And then on page 79, I ask, how would you change the circuit if the design called for a low active output called equal bar? In other words, you want to do the same design, except you want this output here to be low active. Well, think about that. Don't think too hard. This is what you have. Here's the gate right here. When it's high active, there's equal. And this is low, this is low, this is low, low active. That's a NAND gate. There's your NAND gate. How do you change this output gate right here if you want equal to be low? You put a bubble there. The bubble there, and you put a bubble there. And that's how you change the circuit if it calls for a low active output called equal bar. What type of gate is that? Yeah, it's a 4-input AND gate. It's just a 4-input AND gate. But if I draw it like this, it'll work. But it's convoluted. It's convoluted if the engineer draws it this way professionally, because you have a low active signal, it doesn't match a bubble here. And you're trying to figure out what the heck's going on. Up here, you don't do it that way. Up here, you draw the AND gate. You draw the AND gate like this, like a negative input NOR gate. And this says a low here, or a low here, or a low here, or a low there. Gives you a low there. That concludes this lecture.